In the next part of our chapter notes, we're going to discuss the synthesis and reaction of amides, and then continue to nitriles, and then talk a little bit about some significant biological carboxylic acids that have a very distinct structure. We're going to start by looking at how we make amides. Generally, amides are made from a derivative that's above them on the table. So, if we look at the table, we would have acid chlorides above them, acid anhydrides above them, and esters above them. So we could start with any of those three derivatives. And so again, in order to make this compact, I've simply abbreviated the leaving group for those derivatives. And if the leaving group were chlorine, it would be an acid chloride. If it were a carboxylate, it would be an acid anhydride. If it were an alkoxy group, it would be an ester. What we're going to do in this reaction is we're going to put in an amine. And the amine is going to have at least one hydrogen attached to form a stable product. We're also going to put in a base, which typically would be pyridine. However, as we're going to see, pyridine is added just to reabsorb the hydrogen plus after the nucleophile attacks the acyl carbon. And in fact, the amines themselves are bases, so we could just use a large excess of the amine instead of putting in pyridine. And this is really commonly done when the amine is inexpensive and readily available. For example, if our amine is going to be ammonia, we would just use a large excess of ammonia. The end product then would have our acyl group, our C double bond O, and we would have NR2 prime attached. We would have lost one hydrogen from our starting reactant material. The other thing that I want to note here is that I've put R prime 2, just indicating that the carbon groups don't have to be the same, but really we can have any combination of different carbon groups and hydrogens on the nitrogen in this reactant as long as we have at least one hydrogen. So I could have 3 hydrogens, I could have 2 hydrogens and 1 carbon group, I could have 1 hydrogen and 2 carbon groups that are the same, I could have 1 hydrogen and 2 carbon groups that are different. If we look at the mechanism, this reaction follows our basic SN-AC mechanism. We don't need to protonate first. The amine is a strong enough nucleophile that it will react directly with the carbonyl carbon, push a pair of electrons out of the way, and make a tetrahedral intermediate. A pair of electrons would then push down, push out the leaving group. We would end up with this protonated intermediate right here. In order to make it stable, base would come over, it would remove a hydrogen from the nitrogen, forming the stable amide. Again, we typically use pyridine as our base, and in fact, that's the most likely base in a reaction where pyridine is present, but we just write our generic base symbol, not worrying about exactly what the base is, and in fact, if we use a large excess of amine, that would be the base instead of pyridine. Now, one thing that's very confusing about amides when compared to esters is that esters had the Fischer ester synthesis, where we could make an ester directly from the carboxylic acid and the alcohol. That is not generally done with amides. Amides generally cannot be made by direct reaction of a carboxylic acid and an amine. The reason for this is that amines are themselves very strong bases. So when we mix the amine with the carboxylic acid, we get a very rapid acid-base reaction. This forms a carboxylate anion, and it forms an ammonium positive ion. The ammonium ion has 4 bonds and no lone pair. So therefore, it cannot behave as a nucleophile. So it's not capable of reacting directly with that carbonyl carbon anymore. Therefore, Any attempt to try to attach that nitrogen directly to the carboxylic acid is doomed to fail because it's going to do acid-base reaction much more rapidly, and it's going to become something that's not a nucleophile and can no longer attach. We're now going to look at some of the reactions of amides. We're going to start with hydrolysis. Hydrolysis is an extremely important reaction of amides in biochemical systems because there is a class of biomolecules that is built up from chains constructed from amides. That biological molecule is the protein. In our metabolism, when we consume proteins and we want to use them as food, the protein needs to be broken down into its individual pieces. And in order to do that, it is going to be hydrolyzed. The biological organism is going to break apart the amide bonds that form the protein chain. This can occur under both acid and base conditions. We're going to first look at the acid conditions. The acid conditions would involve using aqueous strong acid, in other words, aqueous hydronium. The result of the hydrolysis reaction would be an oxygen molecule from water, an oxygen atom from water would become attached to the carbonyl, the NR2 would be removed and protonated, and then because we're in acid and HNR2 is a strong base, it would be protonated again, and we would get this result right there. This follows a typical PRAM mechanism. We need to first add the water and then remove the NR2. So we are going to protonate, add, make stable, protonate, remove, make stable. Walking through that mechanism quickly then, we've seen this before many times now. You can see we first protonate on the amide. When we protonate the amide, we protonate on the oxygen, not on the nitrogen. We get this intermediate. The water molecule is attracted to the carbonyl carbon. It makes a bond. So that's our add step. We get this intermediate, and then we deprotonate that OH2 to make it stable. And here we go. We get this intermediate. Now we want to remove NR2 prime. So we protonate on the nitrogen. We remove the NR2 prime plus as a leaving group. We get our intermediate, which looks like a carbocation, but is resonance stabilized by the adjacent OH. And then we deprotonate that and get our carboxylic acid. Amides can also be hydrolyzed by base. In order to do this, what we're going to do is we're going to use at least one equivalent of base, for example, sodium hydroxide, in water, and we're going to heat it. We're going to need heat because it turns out this is a relatively difficult reaction to achieve, and it's very slow at room temperature. Furthermore, I want to point out that the actual correct mechanism of this reaction is somewhat different from the mechanism given in the book. So you will need to study the mechanism in our notes in order to properly understand this reaction. This reaction follows a modified form of the SNAC mechanism. So again, in an SNAC mechanism, we're not going to need to protonate first. The hydroxide nucleophile will be a strong enough nucleophile to react directly with the carbonyl carbon of the amide. We will get a tetrahedral intermediate. Now, the problem with this tetrahedral intermediate is that OH minus is a much better leaving group than NR2 minus. If we look at the related pKa's, OH minus has a related pKa of about 15.7, whereas NR2 minus is going to have a related pKa at around 38. So that means that OH minus is 10 to the 20th times as good of a leaving group. Therefore, it's extremely unlikely that we would ever push down and push out Nr2-. That's the mechanism given in our textbook. That mechanism just does not work. Instead, if anything is going to get pushed out, it's going to be hydroxide, which just means that we're going to equilibrate back and forth rapidly here. Push the hydroxide in, then push it back out. Now, once we establish this equilibrium and we have a significant amount of this intermediate, we do have another reaction available to us. OH is a weak base, but it's a base. We do have considerable amount of hydroxide left in the reaction. So what we could get is a Bronsted-Lowry acid-base equilibrium. The base would come over, it would remove this proton, a pair of electrons would go onto that oxygen, and we would get this intermediate. Now, if we look at this intermediate, we can see that now what we have is one OH- here, putting pressure, and a second OH- here, putting pressure. So, in a sense, this is what I would call the super tetrahedral intermediate. So, in fact, I have this little picture here. This is sort of a joke that I make, that this is like, when Red Skull puts on some kind of robotic super skeleton strength kit and becomes much stronger than normal Red Skull. In this case, with this double anion, which is itself inherently much higher potential energy, and the additional electron pressure, we now have enough driving force to push out the very weak Nr2-. That's going to create this, which is just a relatively stable carboxylate, and Nr2- base, which is a very strong base. Now, in theory, the Nr2- base could react again with the carboxylate and go backwards, but in practice, that's going to be a relatively slow reaction. Instead, it's much more likely that it's going to react with a water molecule present in the aqueous sodium hydroxide by acid-base reaction, where this is a really strong base, it's a reasonably strong acid, it deprotonates a water molecule, creates another molecule of hydroxide, creates a molecule of amine, and leaves the carboxylate behind. This would be a much faster reaction than the corresponding reverse reaction, and so what we have is another one of these potential equilibrium where one of the directions is very slow, so effectively it only moves in one direction. It should also be pointed out that we need at least one equivalent of hydroxide because we use one hydroxide for our first addition, we use a second hydroxide for our deprotonation, and actually at the end we make one hydroxide back, but we're still short the second one. We don't make the second one back. We're now going to look at a couple other aspects of amides. First one I want to show you is the hydride reduction of amides. This turns out to go in kind of an unexpected direction. When we take an amide and we react it with lithium aluminum hydride, it turns out that what we're actually going to do is add 2 hydrogens and replace the entire oxygen atom. The nitrogen is going to stay attached, so that what we get at the end is H2 and then whatever amine was attached. We're going to do in our second step not a hydronium, but just water to hydrolyze and protonate everything that needs to be protonated. Because if we put in hydronium, this is a strong enough base that it would react with the hydronium, and we wouldn't get amine, we would get a protonated form of this. We would call that an ammonium. Presumably we would want the amine, so therefore we would have to use water, or we would have to use hydronium and then treat it with base to deprotonate that.